Imagine throwing a ball at a wall and watching it pass right through. In our everyday world, this is absurd. Yet, in the quantum realm, this mind-bending phenomenon, known as quantum tunneling, is not only possible but a fundamental aspect of reality. It's as if particles take a ghostly shortcut through seemingly impenetrable barriers. To understand quantum tunneling, we must delve into the realm of the incredibly small, where the familiar laws of classical physics give way to the strange and counterintuitive rules of quantum mechanics. A cornerstone of this realm is wave-particle duality, the concept that particles like electrons exhibit both wave-like and particle-like properties. When discussing tunneling, it's the wave-like nature that's key. The behavior of these quantum particles is mathematically described by the Schrödinger equation, a fundamental equation that governs how a particle's wave function evolves over time. This wave function doesn't pinpoint a particle's location. Instead, it provides a probability distribution, the likelihood of finding the particle in a specific place. Classical physics dictates that if a particle lacks sufficient energy to surmount a barrier, it will simply bounce back. However, the quantum world operates differently. The wave nature of particles allows their wave functions to extend into and even through barriers, even if the particle's energy is classically insufficient. This means there's a non-zero probability of finding the particle on the other side of the barrier it has tunneled through. This isn't magic, but a probabilistic event. Quantum tunneling doesn't guarantee a particle will pass through a barrier, but it assigns a probability to this occurrence. Several factors influence this probability. Particles' energy: higher energy increases the tunneling probability. Barrier's width: a narrower barrier increases the tunneling probability. Barrier's height: a lower barrier increases the tunneling probability. Particle's mass: a lighter particle has a higher chance of tunneling. Quantum tunneling isn't just a theoretical curiosity, it has tangible applications that impact our lives and our understanding of the universe. Nuclear fusion in stars: at the core of stars, immense pressure and temperature force atomic nuclei together. However, they repel each other due to their positive charges. Quantum tunneling allows them to overcome this repulsion and fuse, releasing vast amounts of energy that power the stars and create heavier elements. Radioactive decay: unstable atomic nuclei decay by emitting particles like alpha particles. Quantum tunneling allows these particles to escape the strong nuclear force binding them within the nucleus, even if they don't classically have enough energy to do so. This process is used in medical imaging and carbon dating. Tunnel diodes: these semiconductor devices exploit quantum tunneling to control electrical current flow. They enable rapid switching speeds in electronic circuits and are used in various applications, including microwave oscillators. Scanning tunneling microscopes, STMs. STMs use quantum tunneling to image surfaces at the atomic level. A sharp tip is brought extremely close to a surface, and electrons tunnel between the tip and the surface. By measuring the tunneling current, the microscope creates an image with atomic resolution, providing unprecedented insights into material structures. DNA mutations: recent research suggests that quantum tunneling may even play a role in DNA mutations. The tunneling of hydrogen atoms can potentially cause errors during DNA replication, leading to mutations. Quantum tunneling is deeply connected to Heisenberg's uncertainty principle, which states that there's a fundamental limit to how precisely we can simultaneously know certain pairs of a particle's properties, like position and momentum. This principle allows a particle to borrow energy for a fleeting moment, which can facilitate tunneling. The mathematical framework for calculating tunneling probability comes from the Schrödinger equation. Solutions to this equation provide the probability of finding a particle in a given location, even within classically forbidden regions. Quantum tunneling has been experimentally confirmed in numerous experiments, most notably the tunneling of electrons through thin insulating layers in tunnel diodes. This phenomenon continues to be a vibrant area of research in physics and chemistry, with scientists exploring its implications in diverse fields like superconductivity, catalysis, and molecular biology. Quantum tunneling is a testament to the strangeness and beauty of the quantum world. It challenges our classical intuitions and reveals a universe far more nuanced and surprising than we might initially imagine. It reminds us that our understanding of reality is constantly evolving and that the quantum realm holds many more secrets waiting to be uncovered.